Hi everyone, Rivera-Adorno here. Welcome back to my channel. Today you're in store for a wonderful crafty science story time as I tell you about the time that I made a dress based on my research to wear said dress to present said research at a conference. Let's go ahead and get started. In order to talk about this, we gotta rewind the clock a little bit. So my research in graduate school was based on studying nanoplastics that were released into the air as a result of a process called cured in place pipe, or CIPP. And you don't need to remember that. All you need to know generally is that it is a process used to restore sewer pipes or stormwater management pipes, all while doing it underground. So you don't have to dig up the pipe and replace the pipe. You can repair the pipe while it's still underground. So this is a process commonly used in a lot of cities and towns and states everywhere to repair these pipes. And we were just testing and observing and studying nanoplastics that are being released into the air as a result of this process. Studying nanoplastics is really tricky. So for one, it's a really new science in the first place. Kind of nanoplastics have really only been talked about for probably the past couple of years. We've known about microplastics for longer, probably since about like the 2000s, but nanoplastics are even more recent than that. Nanoplastics are really, really tiny. In fact, they are nano-sized, which is 1/1000th of a meter. So they're even a lot smaller than microplastics. So the same thing that can be used to study microplastics can't necessarily be used to study nanoplastics. They can be made out of a lot of different materials. First of all, there's just like all sorts of different plastics that exist that when they get broken down can make all sorts of tiny pieces of nanoplastics. Sometimes those different nanoplastics get broken down by like seawater or by wind or by chemical processes. That changes what type of materials they're made out of. Nanoplastics are just really hard to study and they're a relatively new field, so scientists are currently trying to figure out what is the best way to study and learn more about nanoplastics. So when we were doing our research on nanoplastics, we kind of used as many different techniques in our lab as possible. And one of those techniques we used is called STXM. That stands for Scanning Transmission X-ray Microscopy. A lot of big words, let me break it down for us. So this is a type of microscopy. It uses a microscope. If you recall in my video where I discussed about cameras versus microscopes, a simple light microscope uses visible light, so the light we can see, and a bunch of lenses to focus the light to make a really tiny object appear bigger. A Scanning Transmission X-ray microscope, or STXM, does the same thing, but instead of using visible light, so that is light we can see, it uses X-rays, and instead of using lenses that can focus visible light, like a simple light microscope does, it uses special lenses that can focus X-rays. And instead of trying to make a small object appear bigger so that you could just see it, you're actually measuring the amount of light that passes through a tiny particle and you could see it that way. So for example, if I have, this is really crinkly. Aluminum foil is very optically dense. That means that if I were to put it up to like a light, no light is gonna get through it. It's opaque. You can't shine a light through it. Versus something like parchment paper, if I were to hold up to the light, some light is still coming in, but some light is blocked. This has a lower optical density. So in STXM, when you're shining your X-rays through particles, you're measuring those different changes in optical density or how much light is getting through, and you can transfer that information into a picture of your particles. In addition, that's what the transmission part of Scanning Transmission X-ray Microscopy means. And then the scanning part, or the S in STXM, means that instead of moving your light around to get through different particles, means you're actually moving your sample around to get through the beam of X-ray. So that's a very simple explanation of what STXM is. It is using X-rays to view tiny, tiny little particles. Instead of in a simple light microscope, you're using visible light to also view tiny particles. Then you could so now using our STXM, we have pictures of our nanoplastic particles, which means we know what shape they are and what size they are. But if we use another property of X-rays, we can get even more chemical information, which is really exciting. And this is something called NEXAF, or Near Edge X-ray Absorption Fine Structure Spectroscopy. You can forget all those words I just said. Basically what this means is that in addition to when we shine an X-ray through something, it either is letting a little bit of light through or letting no light through, it is also exciting the electrons within the little particle atoms within whatever you're imaging. So remember, if we remember in how Christmas lights work video, where I talked about that if an electron gains energy or loses energy, something crazy happens because electrons just be wild. So when you shine an X-ray on your little particle you're trying to measure, those electrons absorb some of that energy from the X-ray, because the X-ray has a lot of energy, and the electrons want to take that energy. And when they're taking energy, they get really excited. And if they're gaining energy, something's going to happen. And in this case, what happens is on our kind of data readout, you have a little spike appear. And that little spike that appears, and I'll show you some pictures of what a Nexa spectrum looks like. Those little spikes appear. That tells you something important about the chemical composition of your material. So let's say, let me grab my chemistry model kit. As you can see, I have not broken it down from my triglycerides video. So let's say here that we have two carbons attached to each other with a double bond. If an X-ray were to come in and hit this and make the electrons go crazy and cause a little spike on our data readout, because this was a carbon double attached to another carbon, that little spike is going to occur at a certain energy level. And that is what we're measuring with a Nexa spectrum, is where are there spikes at specific energy levels. And the specific energy levels tell us what type of carbon or what type of material we just hit with an X-ray that got excited. So a carbon with two attachments to another carbon is going to be at a specific energy level, whereas, this is a carbon doubly attached to an oxygen. That is going to be excited at a different energy level. And so with all of that information, with different energy levels, with different molecules going crazy inside of our particle, because we hit it with X-rays and those electrons gained energy and went insane, we can get information about what actually is the chemical composition of our particle, which is really, really cool. Not a lot of labs do this because it's a really expensive technique to do, but it's super cool. And then you can take all of that information you just got about chemical composition and you can color code it, and then you can actually like put it onto pictures of your particle, so that if your particle is like made out of different things, but like at different spots, it'll turn up differently on your pictures. So let's say, let me get some markers. No, let me draw on parchment paper. So let's say like, almost kind of like a muffin. Let's say you have a particle that looks like a muffin and it's got like little dots in it, like almost like a chocolate chip or blueberry muffin. The color or how much energy was excited when the X-ray hit this region would have different peaks or different little spikes on the data readout than when it hit this region. So then we can color code our images for the different types of materials at each different point of our particle. So not only can we measure the size of them, see the shape of them, we're also understanding what they're made out of. And when you color code them, it makes really, really pretty pictures, like so. And so back to kind of how I ended up making a dress, is I was getting ready to attend a research conference. And at said research conference, they actually had an art competition. And if you win the art competition, you got like $200. And broke grad student, I want $200. And I'm kind of creative. So I was like, what if I take all of my little particles that I have to present at the conference and I rearrange them in some aesthetically pleasing fashion? And so I came up with this, flashing picture right now, this design, which I thought looked really cool. Printed it out, brought it to the conference, And I won first prize. It was based on popular vote. I won first prize. I got my $200. I was very excited. So then I thought, what if I reinvest this $200, create my own custom fabric from this pattern, and have it printed and shipped to me? And I used the company Spoonflower for this just because it was the one I knew about that you could easily print out and make your own custom pattern. And this is my lovely fabric that I made from my particle images, my particle artwork. And then I thought, now that I have customized fabric made out of my research, I'm gonna make a dress out of my research. And at the time, I had just watched the movie White Christmas for the first time and became obsessed with every single outfit from that movie. But I loved the neckline of the black dress Rosemary Clooney wears in the, like, Love You Didn't Do Right By Me, whatever the name of that song is, scene. And I wanted to recreate that on my dress. So I got to work, started patterning out pieces, started making this dress out of this beautiful material, had it all done, turned out really good, and then I wore it to the semi-annual American Chemical Society research conference and presented my research in said dress. And so at the end slide, I had a picture of this pattern up while I'm wearing a dress patterned after that, and it was kind of my, like, I will never be more extra or more cool than this moment. And it was really awesome. Now, the tragic thing, and you're probably wondering, why am I not currently wearing the dress, is that this dress got lost in the many moves that I made last summer across the country, back and forth. And if you're sad about that, imagine how I feel, because not only did I lose my beautiful, custom-made, custom-printed research particle dress, I also lost a bunch of my other science clothes that I was really happy about. But I do hold up hope that they'll just pop up one day, and then I'll be really happy. So yes, unfortunately, I lost that dress, but I do have the memory of getting to wear it and be super extra in my life, which is fantastic. Hopefully, I really do hope one day it pops up again. Thank you all so much for watching this video. I hope you enjoyed hearing a little bit about this story time, about how when I was an absolute boss serving up great looks at a research conference, I enjoyed getting to tell it. If you are interested in learning anything more or have any questions about STICSM or any of my research, I did put links to my papers I have published below in the description, and I'd be more than happy to answer any questions you have in the comments. I love answering your guys' science questions, comments. You guys ask excellent questions. Thank you again so much for watching. Today's fun fact we're gonna rate is that in addition to nanoplastics, STICSM is also used to study ice nucleation particles and other air pollutants. So drop that rating for the fun fact in the comments below. Please like this video, subscribe to my channel, share it with your friends. I love it when people share what gets them excited with other people. Please follow me on Instagram. I post every Tuesday and Friday, and keep it sciencey.